I'm Michael Ossmann. I am the founder of Great Scott Gadgets. You might know me from projects like Ubertooth and HackRF. Oh yeah, and which just launched on Kickstarter yesterday. Thank you for those of you guys who are contributing. I really appreciate it. I kind of started this project, but mostly my role is getting people together to work on it. So a lot of this is really stuff that these other guys to my right are going to talk about. Dominic, I messed up. Dominic Spill, wave Dominic. He's lead on the Ubertooth project at this point and has been for a while. He's doing a lot of the host code and getting these demos working and stuff with for Daisho, which he's chuckling about. He has some interesting other projects going on, like tapping PS2 keyboards and playing with USB on beagle bones and all kinds of stuff that he'd love to talk to you about if you catch him and buy him a beer. Mike Kershaw, you know him as Dragorn of the Kismet project and creator of the Kisby, which is shown on screen there, which is a Zigbee and 802.15.4 sniffer, all kinds of other cool stuff. He's doing a lot of our hardware design on this project. Oh, and we don't have a slide for Jared here. Wave your hand, Jared. This is Jared Boon. He's not an official speaker for this talk, and we didn't put a slide in here for him because he told us he wasn't coming. And and here he is. So Jared was, he's helped me out a lot with a whole bunch of my projects from early on, like the Ubertooth project. He had a huge part in the HackRF project. He's a major part of the Daisho project, so we dragged him up here. And he's also been quite instrumental in getting our demos working here today. So we decided that he was going to sit up here and talk with us. I'm going to give you a little bit of background about the project. Then we're going to talk about, what we're doing, why, how, and what our progress is so far. This really is a work in progress, but we have a lot of cool stuff to show already. This is a standard disclaimer you'll see on a lot of projects that are funded by the cyber thing, DARPA Cyber Fast Track program started by Mudge. So thanks Mudge and Cyber Fast Track program. We built our first devices, our own boards, our own Mainboard in May, and since then. But a lot of the stuff that we're doing are demos that are partially our own boards and partially commercial development boards, kind of a mishmash of things just to get things working. And so far the bring up of our main board, we'll talk about it a little later. It's going pretty well, but it is a work in progress. And there are a couple of members of our team who are not with us today. Benjamin Vernew, who is also somebody who's contributed a lot to the HackRF project. He's in France at the moment, where he lives. And Marshall Hecht, who is somebody who's had a major role in this project, and we'll talk about his role in the project later on. He's not able to be with us today either. Also, we hang out in the Daisho channel on Freenode, so if you are interested in this project and you want to chat with us, just come drop by IRC anytime. So I had this idea, and this was kind of where this project came from originally. I had this idea that I wanted to build something like this, a USB multi-tool. Something like a little microcontroller based board that had multiple high-speed USB interfaces. So I could connect it, for example, for USB man-in-the-middle stuff. I wanted to have one port connected to a host and another port connected to a device, and be able to emulate a host to the device, be able to emulate a device to the host, and do all kinds of stuff, monitoring, injection, modification of the traffic going between the two, going over the USB bus. And that led me to some other ideas, like putting the USB man-in-the-middle device between two USB devices instead of between a host and a device. You might be able to connect two devices back to back through this special thing. And that you could do some interesting stuff like duplicating flash drives without a host, maybe connecting a Bluetooth adapter to a keyboard and turning it into a Bluetooth keyboard, all kinds of creative things. You could also potentially connect a host to a host through this device and, I don't know, do some kind of networking topologies, all kinds of interesting stuff that you could accomplish. And I'd want like a third USB port for monitoring. So I would need something that's like really small with a microcontroller and 3 high-speed USB ports, preferably embedded, integrated into the microcontroller, something like this. And it didn't really seem like this was going to happen. There weren't a lot of options for a chip that would do what I wanted. And as I kind of explored how I might build something like this, it got bigger and bigger and more expensive, and not really the small thing I wanted. I wanted like something that would fit on my keychain and be a bottle opener. Didn't seem like that was going to happen. So I'm also interested in making a Gigabit Ethernet Tap. I've had the Throwing Star LAN Tap for a long time that only monitors 10 base T and 100 base T. And if you plug it into a Gigabit Ethernet connection, it actually knocks it down to 100 megabit, 100 base TX, and lets you monitor it that way. But people always ask me, hey Mike, when are you going to come out with a Gigabit Ethernet Tap? And it's, my answer has always been, well, when it looks interesting to me, because there are already Gigabit taps on the market. It's relatively straightforward to use a Gigabit Ethernet switch IC, and like one of these chips that's in an Ethernet switch, and find one that supports port mirroring and just configure it for port mirroring and make basically a special purpose small switch that just is a tap. And there are already products on the market that do that. So that makes it less compelling for me. I like trying to do things that other people haven't done before. Also, the Ethernet chips that are out on the market are not really open source friendly. They're not available in small quantities. You generally can't download documentation for them without signing an NDA. So that also kind of tempered my interest in that sort of solution. So, but I have thought about, well, what would be other ways that I could do interesting things with Gigabit Ethernet? And the best way that finally kind of presented itself, and I think mostly it was talking to Dominic some months back that kind of led me to this conclusion, was that we could just plug in PHY ICs. I don't know how many of you guys saw Andrea and Daniela's talk earlier today, but they were talking about PHY and MAC chips for Ethernet. There's the PHY layer chip that's a physical layer, and then there's the MAC layer chip that's the MAC layer that talks to your host computer typically. And they're typically 2 different functions on 2 different chips. So instead of having a MAC and a PHY, we could just get rid of the MAC and just connect the PHY chip to another PHY chip through some programmable logic like an FPGA, field programmable gate array. And if we do this, if we connect multiple PHY chips to an FPGA, it lets us implement our own MAC layer, or even kind of do without a MAC layer and just transfer raw kind of PHY layer data, or it's kind of halfway between PHY and MAC layer data. But it's basically the lowest layer we can get, the GMII interface in this case for Gigabit Ethernet, through the FPGA, where we can control things and we can duplicate data in the FPGA and tap that data at the physical layer or as close to the physical layer as we can, which is a little different than most MAC layer devices like the taps and Ethernet switches that are on the market today. So this was kind of exciting because we could do some things, potentially PHY things that we couldn't do with a MAC layer device. And it would be so much more flexible for the things that we want to do for security research and development. But hey, if we have that kind of an architecture for doing Gigabit Ethernet, why not use the same architecture to do what I wanted to do all along with USB man in the middle? There's a USB PHY chip. The USB 2.0 PHY chips are called ULPIs. So just as an example, we could put a ULPI connected to an FPGA, connected to another ULPI. And we could do the same kind of PHY layer tricks, potentially, with a completely different protocol using the same basic architecture. I just went the wrong direction. So if we were to make it modular, if we have an FPGA-based board that has a high-speed connection to a host computer for doing monitoring and control and so forth, then it would be nice to have a modular front end that has the PHY chips and the connectors for whatever target medium we're interested in, whether that's Gigabit Ethernet or USB or anything else. And that's how the Daisho project was born.
So as you can see, we named it after a pair of swords as to sort of represent the front end and the mainboard pairing, and because we couldn't come up with a better name. So let's talk about what it's actually going to be once we build these things. The idea is we can have a physical layer monitor for multiple technologies. As Mike said, there's Gigabit Ethernet, there's USB, but we also want to look at other things. We're looking at other targets, anything high speed, anything where we can do the data backhaul over USB 3. The idea being that once we've built this platform, we can just build new front end modules in the future to target any additional technology that we want to look at. So we've got some targets within scope for the project, but they're not necessarily the only front end targets we're going to have. Mike and I think everyone in the team is pretty militant about open source, both software and hardware. Almost all of our other projects are open source, and we like to maintain that as a design philosophy. Everything we develop is developed on GitHub or SourceForge or something like that. Everything you see today is already available and has been uploaded to our Git repositories. So you can go and download the hardware designs and the software and play around with it at the moment. Not that it all works, so probably best to wait. Affordable's an interesting term. Obviously, as Mike said, getting a Gigabit Ethernet switch and modifying it to monitor a port, to mirror a port, is fairly cheap. But we think we've got more flexibility, and we don't think there are any other products going to be around that have the similar flexibility that anywhere near the price range that we're looking at. So we're hoping it's going to be within the price range of the hobbyist, the security researcher. I mean, ideally, someone will pick up one of these devices and be able to, as a student, come up with, explore the security of various protocols over Ethernet or various other things, and be able to explore the MAC layer and such. And it'd be really nice if it was bus powered, but I think it's unlikely with the current power requirements. But for some applications, that would be really nice. Again, the HackRF project is bus powered. It's nice to be able to put something in your backpack, pull it out, and just start monitoring a communications channel, not have to worry about a huge rack mounted setup. And do you want me to wave this around?
Or later.
I
just got it out.
Had no idea it was this size. So this is actually a Daisho mainboard that is part built. Let's not look at the back. And this is the sort of size we're looking to target in the future. I have no idea where the extension connector goes.
I'll get that on you.
So,
We'll talk about it later.
Okay, that's fine. That'll come later. But it's going to be about that size, and then the front end modules will be a similar size and mount on top of them. So you're looking at something you can easily carry around in your backpack and take on customer sites or whatever you want to use it for. So I was talking about targets we're looking at, and Mike said Gigabit Ethernet or USB 3. We also want to look at HDMI, because within the next couple of years, HDMI is going to have Ethernet over. I mean, it already supports that. That's going to become far more popular. I think the next generation of games consoles are going to be using, getting their internet connection over HDMI. It's got all sorts of other interesting facets. You know, you can control devices over it as well using CEC. So we like that. And RS232, because we wanted a nice, easy, straightforward. It's all right. We want a nice, easy, straightforward technology that we could use as a proof of concept. So one of the demos I'll be giving later is RS232 tapping, and is probably the most overly engineered RS232 tap you will ever see. But it was a nice proof of concept so we could build something and say, yeah, we know this works, before going on to build complex front-end modules and things like that. And the idea, as I said previously, we add extra targets. So if we suddenly decide we want to build something that looks at DVI video connections, then it's fairly straightforward to build a front end to that, and most of the intelligence is going to be in the bit stream that gets put onto the FPGA on the main board, which we'll already have built and designed. So this is kind of the hard initial part, and then it should be fairly straightforward to add and expand it in the future. So it'll look something like this. The front end module will just have two connectors, and will just sit in the middle of a connection. We don't have a front end board to wave around, do we?
It should look the same from a distance.
Yeah, it doesn't have any connectors on, but from this distance it probably doesn't make much difference. Again, there'll be a picture in a minute. But the idea is that there'll be a similar sort of size, have a couple of connectors on each side, and you'll put it in the middle of a connection, a target connection, and then it will tap the data. We take the physical layer data back to the main board, and in the FPGA we copy it into a buffer, and then pass it back out to the other side of the connection and mirror it to the host. So it's pretty straightforward in terms of the concept. So I'd like to explain why we're doing this, because that's the most common question we get. And this is Wright's law from Josh Wright. And we feel if we quote it often enough, it will become actually Wright's law. If you Google it, you'll find a lawyer whose surname is Wright, who has a legal company called Wright's Law. And the idea being that until we can explore the attack surface, until you can attack something at the physical layer or at any other level, you can't be sure it's secure. You can look at a spec and say, yeah, I think it's probably pretty secure. Yeah, we avoided these traps and things like that. But until someone can go and probe it and say, well, is this implementation compliant? Does this really work? Then we're not going to know that a device or a protocol is secure. And I think most of the work we do conforms to this. And for example, Wi-Fi connections have often had monitor mode and promiscuous mode from the early days of Wi-Fi cards. And that ability meant that we could go and explore the flaws in WEP and defeat it. And so the manufacturers were forced to start implementing WPA. And then the flaws in that have been shown. And we now have WPA2 in almost every device that you can buy on the market today. But as a counterexample, and I'm aware this is mostly my responsibility as a developer on Ubuntu, but the Bluetooth pin scheme is incredibly weak. It was shown to be vulnerable back in 2006, I believe. And they came out with a new version called Secure Simple Pairing. But I guarantee you can go out to any electronics store now and buy a headset that uses the old pin sharing method to connect devices, because there's no excellent black hat talk that someone's come out and said, well, look, this is all vulnerable, and here I can own a headset and a phone within minutes or something like that. And as soon as you can give that talk, as soon as you can show that research has been done, then the device manufacturers will be forced by consumers to use the more secure methods. So we think that's kind of the important point here, is that we're building tools to enable that research so that we can make things more secure in the future. I think I've mostly said what this slide says. So the only thing to add is affordability. We know there are USB 3 network sniffers. We know there are Gigabit Ethernet network sniffers. But if it's going to cost you several $1,000s and you need university or government funding in order to get one, then it's less likely that the right people are necessarily going to get it. We want this to be open to any researcher who has a good idea. And the smart people don't always have the biggest funding. So we're hoping that it might be at least within range of someone who's really smart about looking for flaws in these things. So everything's on GitHub. The tools, the reason it says where possible after tools here is that we can't use open source tools for FPGA development. We have to use the tools from the vendor. But what we have, we've chosen a part that can be used with the free tools. So the idea being that anyone who wants to get involved and join in with the project can, at zero cost, start building these images for the FPGA. But unfortunately, as yet, there are no open source FPGA tools available. There are a couple of projects that have been started, but they're obviously fighting a very, very tough battle with the main vendors. So for USB, there's a fantastic device called the Beagle from Total Phase. It's an excellent piece of kit. We've been using it to debug our Bluetooth. Not Bluetooth. I don't know where I'm going with that. Debug our USB stack, but it's incredibly expensive, and the same thing goes. It's not open source. You can't get in there and tinker with it. It's a completely closed box, and fantastic if you can get hold of one and you want to debug your implementation. But we think other people might want to get in there and fuzz an implementation or play around with it, and we'd like them to be able to build that with our tools. And we'd like to as I say, encourage new researchers. Earlier today, Andrea and Daniel gave their talk about Ethernet packet injection. It was packets in packets on Ethernet. It was a fantastic talk. Try and see the video if you didn't get a chance. But in that, they said they would like to migrate that attack to our Daisho platform at some point. And I think they're getting involved in the project and going to have a look at how they can use our method and our hardware to implement that attack and inject packets into an Ethernet connection. That makes a lot of noise. So is this still me? Yeah? You jump up?
So we did a two-part design, as we mentioned. So it's an FPGA main board connected by USB 3. So the FPGA can do all the signal handling and some of the DSP and some of the other decoding really quickly, and then hand that up to the OS through an enormous bandwidth channel, pretty much the fastest you can get other than Thunderbolt. And I don't think the Thunderbolt specs are really open for developing. So we have multiple front ends on that'll develop for different physical layers. So it's pretty much the FPGA has the RAM, it has an ARM processor for bootloading it, and USB to the host, and then an arbitrary number of PHYs depending on the front board connected to that. So our development hardware is a Terazic DE2-115, which has a Altera FPGA. Oh, you're a brave man moving the demo. So it's a fancy board. It's got lots of blinky lights on it. It's pretty cool. It's got a low-speed 2x20 header, like a parallel port, not parallel port, parallel IDE. And it's got a high-speed mezzanine connector, which we use for most of the things. It's well supported by a lot of development tools, is why we picked it. It'll bootstrap the front-end development until we have our own main board going. So, there we go. They're relatively inexpensive if you ever want to do FPGA development.
This is I'll take on flat UI.
But the downsides of it is the mezzanine connector can't handle high-speed comms that are high-speed enough for what we need, just because of the way their development board was designed. It's not particularly portable. It runs off a 12-volt power supply. It's a closed design. It's great, but it's not what we wanted for the final development. So for the front-end boards so far, we have hardware. The RS232 is our simplest front-end board. It's just a couple of 232 level shifters, pretty much, and two pairs of ports. It's extremely low speed compared to all the other boards, but it's great for testing. It's a 2-layer PCB. I think it's our only board that's only 2 layers, and I think the final version is 4 layers actually. So I'm already lying to you. So we pretty much for this just convert 232 to TTL. If anyone's familiar with RS232, it's plus minus 12 volts, and then for microcontroller level stuff, you can just shift it down. We monitor all the signals, so not just transmit and receive, but all the alternate handshake signals and whatnot we map through. We can jumper across certain connectors, so if you don't want to deal with decoding, DTS or whatever, you can just jumper that across. Right now we're using the 2x20 connector, or 2x40 connector on the DE2. In the final design, we're using the mezzanine connector, so it'll just socket together in a nice stack. So It's a pretty simple PCB layout for this one. Just 2 layers, you know, with the 2 connectors. And there's one in reality. We have it sitting up here, but we probably shouldn't try to move it. So for Giggy, it was a much more complex board. So we have 2 independent Giggy 5-layer chips that'll do 10, 100, and 1,000. So we dump the packets to the FPGA and then write them back out to the other side of the connector. We're using integrated jack magnetics, so you just solder down one connector and it's plug and go. It's more complicated. It's a 4-layer PCB, but it's still pretty reasonable to develop to assemble on your own or get made through like Osh Park or something. So that's the PCB design on that one. We also do PoE pass-through on it. And then we have the physical board made. And then so our goals for that are tapping 1 gig Ethernet, which can't be passively tapped since it randomly assigns different directions to different pairs and whatnot, so you can't just split it out like you can with 10 and 100. We're also going to do very high precision time stamping of packets, so we'll be able to determine exactly how long a round trip to the server at the other end took before it came back and replied, things like that. And we'll be able to do invisible monitoring since we're not at the MAC layer, we're not an Ethernet device as far as the Ethernet network is concerned, whereas we're as close as we can get to raw electrical monitoring. So the PHY transceiver chip will transcode the bit stream and does the electrical talking. The MAC layer is what gives you, the MAC address, obviously, and Ethernet frames and whatnot. So as far as we know, all the existing hardware has a MAC layer. So anything that does, port mirroring and whatnot, it's a switch. It's got an Ethernet address. It's on the network in some degree, so it's detectable. We don't have that, so we should be completely invisible. So we care about it because, as I mentioned, everyone already out there has the MAC layer on it. So bridging obviously is very detectable since you're interfering with the spanning tree and whatnot. And so we want to be as close to passive as we can possibly be. For the HDMI tap, we're looking at 2 HDMI ports for in and out. So we're using a high-speed SerDes chip to split the serialized HDMI stream into a large number of parallel bit streams, so we can handle we can use a much lower power FPGA for it. So this is one of the more complex boards. It's 6-layer design. It's very high speed. It's difficult to hand assemble, but it's still doable. So we're hoping to be able to get at least 1080p. We may even be able to get 4K. So it's currently straining the capability of the DE2, but with the final main board, it'll be okay. So there's other ways to sniff HDMI. There's a bunch of boards out there that do it. The NETV does it, for example, from Bunny, but they can only do 720p or 1080i. You need a really, really fast FPGA to plumb the HDMI directly into you. Since we're converting it into much slower parallel data, we can use, cheaper components and a slower FPGA. So that's the HDMI board so far. It's not quite finished. And HDMI is very interesting because, as Mike mentioned, it's a complicated protocol. There's a lot of things that are going to be using it more in the future. There's bidirectional communication on it. There's a 100 meg Ethernet channel embedded in it. There's basically an I2C communication system between your devices and your TV for transmitting resolutions and whatnot. There's a lot of interesting things going on in there, so we don't think there's anything else that exposes all of that, so it'll be very interesting to see what there is. And then Jared can talk about the main board.
So I did the design on the main board, which, as has already been described, is pretty much the data pump for the entire system. The idea is for it to move data to and from whatever front end board you've attached into and out of, move the data into and out of your host. So it's got an FPGA right in the center. It's an Altera Cyclone 4, EP4CE30. It's a 780 pin BGA, so it's got tons and tons and tons of pins. They're 1 millimeter spacing, and somehow Mr. Ossmann soldered it. We've also got a USB 3.0 super speed PHY attached to the FPGA, and that's how we get all the data into and out of the host. We've got a DDR2 slot, which is, I think it'll function up to 4 gigabytes worth of RAM, and a NXP microcontroller, which kind of orchestrates bringing up the entire board. There's about, I think, 4 or 5 different voltages that need to be on the board in order to power all the different components. So it's important to sequence those as the board is powered up. and make sure that they're done in the correct order. There's also an SD card slot, micro SD, which is where we would store the bit stream to load into the FPGA to give it whatever characteristics it needs to perform whatever attacks you're targeting. Let's see, what else have we got in here? I think that's about it. Front-end connector is actually on the back. It turned out to be pretty much the easiest way to get everything on such a small board. So this is kind of an Xray view of the design of the board. It was done using 8 layers and software called kicad, which, or some people pronounce it kicad. You can see pretty much all of the signals are emanating from the FPGA because it's effectively the nexus for all the data that transfers through the system. And then there's a very strong flow from the USB chip on the left into the FPGA in the middle. This is a picture of the board before it was assembled completely. It looks like there's a few components on the board. Yeah. A very good way to, when you're bringing up a new piece of hardware, is to build it incrementally so you don't wind up blowing up your $50 FPGA because it turns out you screwed something very simple up in the power subsystem. And there it is, fully assembled. Not much to say about that, actually. So Dragorn will tell you more about the CAD tools that we used, since he's as familiar as I am with the pain involved.
So there's a ton of CAD tools out there to pick from. There's the commercial stuff like Altium and whatnot. There's Eagle, which is sort of free, but not really. And then there's a couple of pure GPL tools. We went with KiCad. It's fully GPL. There's no weird licensing. There's no size limits on it. So it seemed a good choice at the time. This kind of says it all. So KiCad is really good in a lot of ways. It's capable of, n-layer boards. So Eagle, if you want to do more than 2 layers, you're paying a lot of licensing fees, things like that. So KiCad, you can do any number of layers. I think pretty much as much RAM as you have, it can do that many layers. There's no size restrictions. You can make your PCB as big as you need. The file format is friendly-ish. It's all text, so it cooperates very well with Git and Subversion and whatnot. You can edit them. Sometimes you have to. It's truly open source, so you get all the benefits of the fine open source GUI. But on the other hand, you can fix bugs in it and whatnot, so it's handy. You never truly get backed into a corner if you're willing to put in the time. It has to mean you're willing to put in the time. Unfortunately, sometimes KiCad does some odd things. I'm not sure what it did.
They're kind of
yeah, I might frame that one. You can kind of see to the side a little bit of the rest of the circuit, and then it just decided one of those pads needed to be really big. So there's some significant challenges with KiCad. Right now, they haven't had a stable release in a little over a year. The development version changed the file format, so you can go from stable development, but you can't go back. So right now, some of our boards are in the new version, and some of them are in the old version. It's not very good at moving components once they're placed, so expect some pain when you're doing layout. And there's no helpful tools for doing things like length matching, high-speed parallel lines. There's nothing that helps you route out of the BGA and whatnot. So I kind of feel like for some of the complex designs we're doing, it feels a bit write-only, where you can make the board, but if you have to go back and edit it, you're going to be a very sad person, which really makes Jared's work on the main board incredibly impressive. So some of those challenges we had in designing the boards, high-speed digital signals behave very oddly sometimes. They act a bit more like analog and RF at that point. The FAB requirements become a fundamental part of your design. Jared had to go back and redesign some of the main board trace widths specifically for the FAB house we use to make them. So you need to really talk. You need to be able to talk to whoever you have manufacturing your circuit boards once you get up to the high-speed multi-layer stuff. For these boards, home assembly is still possible, as Mike Ossmann proved. It's kind of ridiculous that he managed to do that, I think. You probably wouldn't want to unless you're really dedicated. And unfortunately, once you get above more than 4 layers on a circuit board, prototype-sized runs are incredibly expensive. They can still be done, but you're talking a couple $1,000, $5,000 for a dozen boards. So for our requirements, many of the designs with the BGA, need more than 4-layer, which puts us outside of most of the prototype fabs. So we couldn't use OshPark, we couldn't use batch PCB or anyone like that. We also had to do what's called via and pad, where some of the holes through the circuit board go through the pads that the components are on, which is, I believe you said it almost doubles the cost?
Something like that.
Yeah, it's something like doubles the cost of making the boards at prototype size. So we had to work with the fab on the layer stack up. What layers went where, how thick each layer was, because it affects the impedance and whatnot. So high speed signals would get corrupted if we didn't organize that. So if you're doing high speed board design on your own, you need to pick a fab that'll actually talk to you with it about their exact specs. And then so for our main board, it's 8 copper layers. And then, well, these are just, they're interesting numbers. Other than that, it's boring. And then the mainboard firmware is mostly being developed by Marshall, who couldn't be here. But we believe it's the world's first open source USB 3 core. So all the USB 3 handling is done on the FPGA, and that's all in the Git repository. And it's the minimal implementation of what we need to shove the raw data up to the host. So right now we don't need independent bit streams for each FPGA or each front end, but there is a small I2C in the design on each front end board. So when you plug it in, the processor on the main board will automatically detect what's been plugged into it and then load the appropriate code from the SD card. So if there's a front end that needs all the space in the FPGA, it can have its own file and it'll get automatically programmed when you boot. And then on the software side, there's libdaisho, which Dominic is writing, which is a user space driver based on libUSB, so it should be compatible across other platforms as well, like Windows and OS X. And then for Wireshark integration, we're using a system Mike Ryan and I developed called XCAP, which we're hoping to merge into the Wireshark main code very soon, which allows external capture programs to appear as if they were network devices to Wireshark and allow you to directly capture from them inside the GUI, and that'll be part of our demo. So yeah, the XCAP stuff is still under development. Basically, it just allows an external tool to export a simple GUI, and then Wireshark rolls that into the GTK GUI, so it all looks integrated and pretty. So, just a couple quick examples of that. Your standard Wireshark capture config window, and then there's just some random tools from a previous demo. So on the software side, the USB 3 enumeration, we can completely control that. So we could even present an Ethernet device to the host for capturing Ethernet, or we could present the consistent raw data below Ethernet layer and then translate it on the host if we wanted. It is possible for front end boards to, we could present 2 CDC ACMs or whatever. So we have several options on that depending on if you want to present sniffed Ethernet data or if you want to present high timestamp precision raw PHY layer data. And now the scary part.
Wish us luck. Yeah. I wasn't nervous until this moment. All right. There are 2 demos. One is going to be RS232, which I expect you all to be incredibly thrilled about. What we're going to do here is we've got a front-end module that's got 2 USB to RS232. Oh, really? Picking up the demo board. So it's got these USB to RS232 adapters, standard thing you buy for $10, and they plug into our front end. Data goes through the FPGA on the D2, and then back out of the other one, and then we tap it to the host using our own USB stack that Marshall's written, and we use libdaisho. Now this one does not have the world's prettiest GUI, so let me see what I can. So just to prove that we've got two serial connections connected to each other back to back. If I type in one down here, it appears in the other one, and if I go up to here, it appears in the first. And now let me. Oh. So I should be able to just run ./Daisho RS232, and this will dump some information. So what we're seeing here, as I type in one of these windows, is you'll see the characters obviously not translated through, but what you're seeing is the data is going over RS232. We're then copying the signals on all of the lines on that connection and dumping them all with a timestamp every time there's a change. So essentially what we get there is a a sort of logic analyzer for the RS232 port, and that will show us. We can then interpret that data into ASCII or whatever other data we might have going over that connection. There's no limitation on it being a specific format or anything like that. It can be whatever's going over that wire. It could be a completely custom protocol that just happens to be using the same connectors and voltage levels to move stuff around. And then we can just interpret that from the timestamps and transform that into a binary waveform to show us the data shifting around. I went to the bar last night rather than writing the waveform viewer for that. So unfortunately, this is as good as the RS232 demo gets, which is.
What, the fifth byte? Ones and zeros.
Oh yeah, I'm sorry. This byte just here, you'll notice that this switches between ones and zeros, and that is our bit. That's our transmit bit as we go through in one direction. And if I move data in the opposite direction. Oh, wrong one. Why? Oh, yeah. Oh, that was the right one. You'll notice that this bit here is changing instead, and that's the transmit line in the opposite direction. And so as long as you monitor those two, you can then take the timing gaps to work out your bit time and things like that. And you can write code here to attempt to automatically determine baud rate, although if you know the baud rate, then it's really easy to write code to convert this to printable data. So that's the RS232 demo. I know, rocking. Ethernet. So this is the one we finished writing about 2 hours ago. And I'm slightly more confident in this. Hopefully. So if we can switch the serial connector over. Let's turn it off before we. We've only got one serial device. So I'll explain what we're doing here. We have two BeagleBones from TI, lovely little open source boards, and we're using them to just they ping each other, and they're connected to the Gigabit Ethernet board front end that's also connected to the DE2, and then we're backhauling the data. Now, our USB connector for the DE2 uses the same onboard connection as the Gigabit Ethernet front-end module, so we can't have them both plugged in at the same time. So we're actually doing data backhaul to the host using RS232 because we had an RS232 board and it seemed like we may as well use that to send the data back. So what we actually do is take the data in half byte at a time and convert that to a hex representation in ASCII. Then we send that over RS232. The host then converts it back to binary, reassembles the bytes in the right order, and then dumps that into a PCAP, which hopefully, using the external capture stuff that Mike Kershaw and Mike Ryan wrote for Wireshark, should mean that we can monitor this connection with Wireshark. Yeah. Just understanding what the demo was going to do took half the time. Okay, right, Wireshark. So, oh, it's shown up on the wrong screen. Okay, that's not. Yeah, that's very vaguely readable. So we're using not that one. These two devices to capture, and if everyone could cross their fingers. That doesn't look like it worked. Oh. Okay, so this demo didn't work, and it was the one I was more confident in, and I'm sorry about that. It's a bit of a failure. Well, you can see. So here you can see these being dumped over serial. So these are the packets as they come through. The 555 at the beginning is the preamble that you wouldn't normally see if you dump these things with TCP dump or something like that, because that gets stripped off by the MAC layer in your card. So we are getting more data than you would get with a standard network tapping methodology. And you can see that data coming through. I'm almost certain that the problem. I think the problem is probably that I'm also showing them in a serial console. Yeah, that'll cool. Yeah, that'll totally not work. Okay, let's try it again. Okay. Let me say I'm just going to kill Wireshark. There you go. Cannot open serial device. I should have looked at the error messages. Wow. Who knew printf was so useful? All right. There we go.
Hey. Can you see the preamble in Wireshark?
So,
No.
I was about to address exactly that problem. So what you can see here is I've chopped off the preamble in my code, which is something I don't really want to do, to fit it into the link type for Ethernet that Wireshark used by default, or libpcap uses. We have to go to the TCP dump mailing list and run that gauntlet in order to get a second link type that is physical layer Ethernet, because no one's requested one yet, which makes me believe we're the first people to build a tap like this that integrates with these tools, because otherwise they would have requested it before. But it's feasible that in the future we'll have things that are dumped into Wireshark, including the preamble and any extra interesting data or noise that we see around it, which will help debug connections at an even lower layer than is currently possible. So on that note, we should probably go back. Oh, I have no idea where the slides are. There we go. All right. So over the next couple of months, we need to finish building the main boards. We've only got 1.5 built so far, so we need to build some others. There are a couple of corrections that we need to make to the designs. We need to build the HDMI front end, and then we need to take our current front ends for the Gigabit Ethernet and HDMI and retarget them once we've worked out some of the development kinks to use our main board rather than the DE2 development board. We're then going to look at a USB 3 front-end board, which we weren't able to use with the DE2 because, as Dragon said, there's not enough space on the connector for us to get all the signals through. And we're going to do things like identify the front end when you plug it in so that we can load the appropriate bit stream from the SD card and things like that. So you won't have to have a host controlling this stuff. You'll be able to take the board and the front end and just have an SD card with all your different bit streams on and switch over the front end boards, and it'll just handle it automatically as it powers up. As I said earlier, the idea of it being extensible is that we can add additional targets with very low effort. So we can look at things like DisplayPort and DVI and other protocols that you use. I'm particularly interested in the telephone DSL idea, just going up to the outside of someone's house and clipping on a couple of alligator clips to their phone line and just pulling in everything. And I imagine you want to talk about SDR. I'll let you go for it.
Yeah, I really like that idea of tapping phone lines and getting like audio and DSL at the same time. That's really cool. And one of the possible applications that several of us up here, we're all interested in down the road is doing more high-speed, wideband, software-defined radio applications. The HackRF project that I'm launching right now is pretty wide band compared to a lot of the SDR solutions out there. It's 20 megahertz of bandwidth. So if you imagine like your FM radio stations are only 200 kilohertz apart, so 20 megahertz of bandwidth is 100 times wider than that, and it's enough to capture something like an 802.11g packet. But it's not enough to capture like an 802.11n 40 megahertz wide channel, or the new 802.11 AC standard that's coming out that can have up to 160 megahertz wide channels. Some of this stuff that's coming out now is the higher speed communication systems are super wide bandwidth, and there's really no way that we can do software defined radio with a general purpose computer unless we take advantage of things like the FPGA and the USB 3.0 connection that we have available to us on the Daisho. So like one thing I really want to do is monitoring the entire 2.4 gigahertz ISM band so that we can decode all Bluetooth packets from all nearby Bluetooth devices all at once, instead of trying to hop along with them, which is what we try to do with the Ubertooth project with mixed success. And then down the road, I'd like to see Some of us up here have some other plans for this platform that we want to use it for totally unrelated things. If you're an electronics designer and you have any interest in a platform that gives you USB 3.0 connectivity with FPGA, then the Daisho platform might be right for a whole variety of projects. Anything where you want to get data in and out of a USB attached system at the absolute highest rate possible. I mean, USB 3.0 is about 10 times faster than USB 2.0. So it's really an exciting thing to be producing this open source platform for USB 3.0, even though it's a big, complicated project. It's really big for us, and we wouldn't be able to take this on and have this cast of thousands working on this project and be building 8-layer circuit boards without financial support. So our big thanks to the DARPA Cyber Fast Track program and Bit Systems. These guys have been terrific. We really thank Mudge for kicking off that whole project. And I don't know, I don't have a whole lot to say about that other than they're awesome. Thank you. And I think we have a little bit of time for questions, maybe 5 minutes. Any questions out there? Shoot.
Were you not able to do some of the things you wanted to do with the face dancer board by Travis Goodspeed?
Yes, good question. Face Dancer by Travis Goodspeed. The Face Dancer board does implement some of the things that I wanted to do with my original concept for a USB man in the middle, or a USB multi-tool board. The Face Dancer board allows you to connect as a device to your host computer where you're controlling it from, and then also connect as a device to a target computer that you can attack or emulate a device connected to. So some of the stuff that I'm interested in doing has been implemented using the Face Dancer. There are also some folks who have implemented similar things using the Linux USB gadget stack with Android devices in particular, and some other platforms as well. Dominic's been working on something with the BeagleBone Black, actually, that we'll probably be talking about at a future event. So yeah, the Face Dancer is really cool. I definitely recommend checking it out, and it's a lower cost way to do some of the stuff that we're doing, but not all of the stuff that we're doing. Our focus for this project is primarily on getting to the physical layer. We've had tools for years that give us high layer monitoring. Like you can run Wireshark on your host computer and capture something from your Ethernet port or your USB port, but it's only what the host OS sees. And then you can use a network tap of some kind that gives you a little lower level access, but typically that's only MAC layer access and not physical layer access. And if we get one layer, we basically get all the layers above it. So why not target the very bottommost layer we possibly can, and that's the physical layer, and that's what we're trying to get to with this project, and make that technique available to as many different target media as possible. Any other questions? One on the right.
Sorry, I missed the beginning of the talk. How is what you're doing different from a digital oscilloscope, which you can buy off the shelf and it's really erected in software, take the oscilloscope face and turn it back into control?
Right, good question. How is what we're doing different from using like a high-speed digital oscilloscope and pulling bits off of it, pulling a waveform off of it, and then analyzing that in software? To some extent, some of the things that we're doing are very similar to that approach, but generally for the high-speed communication systems that we're targeting, like USB 3.0 and HDMI, we're dealing with systems that are multiple gigabits per second on a wire. And in order to do that kind of approach with a digital oscilloscope requires a big expensive oscilloscope. We're trying to make a platform, it's a little higher, it's going to end up being a little higher cost than most of the stuff that we work on, but we're looking at like the few $100 range instead of the few tens of thousands of dollars range. So we're trying to make something smaller, more portable, and lower cost, and we're able to make it, we're able to achieve those goals primarily by using the off-the-shelf PHY chips for particular target technologies that we put on the front end board instead of having a general purpose high-speed sampler in the form of like an oscilloscope. One more.
Do you envision a sort of a renaissance in fuzzing technologies when it comes to manipulating the hardware layer that is not accessible to any of us without something like this?
That's a good question too. Do we envision a renaissance in fuzzing for attacking hardware layer? I definitely think we have that in mind. That we hope to enable much more research and development in investigation of the security of protocols from the lowest possible layer, layers that have been ignored before. And like Dominic mentioned earlier, Andrea and Daniela's talk from this morning was a fantastic example of that, where they implemented an attack on wired Ethernet, and they were doing 100 base T, where 100 base TX, where we're targeting to support of Gigabit as well with Daisho. But they found an attack that they could execute against, multiple attacks actually, against wired Ethernet that nobody found before. And the reason they found it is because they were exploring the physical layer, where in the past people have only explored down to the MAC layer. So we're hoping to enable that for all target media that we possibly can. And we think that there will be tremendous opportunities for fuzzing and other types of exploration of those attack surfaces. Thanks a lot, everybody.